everyone. Welcome to our webinar on understanding your mine site water balance. I'm Martin Drager with Water Services and Technologies in Canada. And with me, I have Vinicius Araújo from Brazil. So a little bit about our company. So back in 2017, Dr. Nilsson Giger, who some of you may know as the founder of a very popular finite difference model called visual mod flow, as well as other numerical modeling solutions such as FlowPath, decided to open an office in Florianopolis and Belo Horizonte, and with a prime focus on supporting industry or any organization with their water problems. This particular region, we had a lot of focus on mining companies, helping with their water supply, understanding their water budget, and also looking at how to take vast amounts of data and incorporate it into a data management tool that could be used for compliance reporting and on-site practices. Later, in 2022, we opened an office in Kazakhstan, again, focused on supporting mining operations with their water supply, water resources challenges. And just this year, myself and Stella Debebe opened an office here in Waterloo, Ontario, Canada, at the heart of mining in North America. Now, the company is stacked with real experts in hydrogeology, engineering. We have geotechnical experts, extreme advanced numerical modeling experts, and also software engineers that are very familiar with digital architecture design. And I can't forget aqueous geochemical experts as well. The sectors we focus on are mining, water resources, water and sanitation, industrial, and energy. But for the purpose of this presentation, we'll be focusing purely on the mining side. What we do in mining, we really help mines in all elements of water management. Anything that touches or has to do with water, we help with. From our experts in hydrogeology and hydrology, we also help in the hydrogeotechnical side and aqueous geochemical side. And as mentioned, the data management side has become a big service area for us, helping mines to get all of their vast amounts of data into some consumable format that can be used for on-site use and also for reporting around compliance. Now, let's take a brief look at the state of the mining industry. We all know that there's been an incredible change in energy consumption, primarily due to environmental regulation around global climate change and initiatives around reducing greenhouse gases. And so, therefore, plus we've had some unfortunate issues in Eastern Europe with some wars going on that's really impacted the demand for alternative energy sources, which has really driven a lot of the lithium market. But outside of lithium, which is an extreme example, there have been predicted lots of growth from now until 2040 for a lot of the ores that are being processed on a daily basis. And we see, for example, using back lithium, 42% increase by 2040 in production. And we have increases across the board, and which really means that there's going to be an increase in demand for water and also an increased demand for compliance reporting around the ESG initiatives. So continued growth in mining industry coupled with commitments to sustainability are really driving the need for really quantifying water resilience. And further to that, as a service provider to many mining companies, we're always ears down to the ground, listening to customers and asking, what is it you need? And these are the types of things we're hearing. How can we make or take better control of our site water balance and our site risks related to water? And what are the tools available to really efficiently gaining a deeper understanding of water and how it's used across the site and how we can reduce the impacts offsite? And how can we see the interaction between water uses across the site? Sites are very dynamic. Mine sites are constantly changing in their footprint. And so as are the uses, water uses and water sources. So how do we get a better understanding of that? And then also anticipate risk scenarios to plan better. Example, global climate change. We're seeing impacts from flooding and understanding those risks as they relate to water is very important to mines. And of course, lastly, they want to understand the big picture of their entire water balance, their entire site, and not just one particular site. There could be, corporate office wants a view of multiple sites now. So what does this all mean? And why do mines actually care to begin with? Well, obviously, there's a direct correlation between water and operational efficiency production. So when mines are operating, there's a lot of water being used. And the question becomes, what happens if one of the pumping wells that are providing water goes down? How does that lack of water affect all the elements of the mine site? Water resilience, climate impacts. Ironically, I'm sitting here in Waterloo, Ontario, Canada, and it's February. The end of February, we're supposed to be in our coldest, darkest winter months. Instead of being minus 15, it's plus 15, and it's been thunderstorming for the past couple of days. So these things are real, and they're happening globally, and mines have to plan and understand how these climatic changes are impacting their site. Obviously, regulatory compliance is a driver in why mines care about water balance. Effluent volumes and release volumes are really driven by regulatory compliance. And also we have now this new, relatively new initiative around sustainability and ESG goals that are really driving mines to not only do better for the environment and for their employees and for the communities, but also really build their reputation on a public level to get investment. And these are all related to and can be related to the water balance. Obviously, community impact is also an important part. If you don't know what's going on your site, you don't probably know what's going off your site. So these are all things that mines care about as it relates to water balance. Now, they're saying all of these things and we're seeing things, but what's actually happening out there? What is actually the trend? And for me, it's clear mines are committed. They're committed. And we see that organizations, now one of the largest lithium producers is, it's committed to reducing its lithium water use for lithium mining by 65% by 2040. Did we see that 10 years ago? Probably not. Glencore, they've got a target of a water withdrawal of 23%. Now that was hit. Barrick Gold in 2022, they were looking at more reuse, recycled water, 83%. Fantastic. And Vale reduction by 27% in their freshwater use. And the story goes on and on and on. And you can see this on the corporate profiles of many mine sites. So there is a commitment, and that commitment directly stems into the understanding of water, how it's used, the volume of water that's used, the quality of water that's used on a mine site. So just a quick overview here of the water balance. This picture is a depiction. It's a very typical depiction of a mine site. Each one of those dots represents either a water entry point, could be a journey point between water uses, and water discharge point offsite, could be even on-site. But all of these interconnections are very complex when you add on values such as volume data. You add on values such as flux or concentration data. And you add all those elements to every one of these points and make changes to those. It's a very complex, interconnected environment, a water web. And the greater the operational processes, the more need for better control and understanding on a site-wide basis and off-site. Water balance, by its very description, is basically watering. If you imagine accounting for one water drop entering a system and following that water drop as it's moving and it's journeying through the mine site, and how that water drop is discharged off-site. So we're trying to, in a water balance, control, track, understand, and predict and optimize all elements around that water drop. Now, there are ways people break up this water balance. I like to break it up into three segments. One is operational. So what's important operationally from a water balance perspective? So as mining operations proceed each day, there's equipment that's being used. What if one of the dewatering wells requires maintenance or unexpectedly breaks down? What and how do mine operators respond to those changes? The lack of water, for example, or too much water in this case. What about if an ore processing facility has to shut down for whatever reason, replace parts? How is the water going to be redistributed until that facility has been corrected, fixed? And tailing ponds, what about if there's a maximum criteria for tailing pond water level? What happens in the case where the climate changes and there's an increase, a flood event, and there's too much water? So operationally, meaning how anything that impacts the operation water-wise is a very important thing to map out and understand. Another external influence would be regulatory influences that bring more complexity into the equation. New regulations may require a reduction in effluent being released into a river. And as a mine owner and someone who's responsible for daily production, those things matter. And sometimes they're unexpected, they're unplanned. Other times you can plan for them. And that's the beauty of having a predefined water balance, is really understanding and having the ability to anticipate changes before they occur or when they occur. The next level we'll talk about is climate change, something that is very complex in itself, but directly impacts mines. But how can mines right now effectively understand their water risks, and how can they mitigate them? They can't wait for weather. They have to anticipate, model, and understand. So one of the ways a water balance can help in this regard is allowing them to stress the water balance itself. What happens to the system if we've got a lack of water? We've got drought conditions. What happens if we've got a flood event and too much water? How can we quantify these things and predict what's going to happen, not just at one point, but remember, we're talking about a number of complex elements within the site that all need to be considered in the calculations. So the question is, we've got an increase in demand of mining that's going to continue to grow over time. We've got an increased commitment in ESG goals, sustainability goals. We have an increase in demand for certain types of ore that require a lot of water. What and how, where do we start? It's very complex. There's all these elements that we need to consider. So it can be very simplistic as we talk about it in a webinar, but let's go through that. The first step to a water balance is to develop a complete field survey and understand and quantify all of the various sources of water, areas that are storing water, and areas that are releasing water. And this is purely going into the field, making sure every single element is captured in some format. And then, of course, to make sure that we're evaluating the measurements themselves and collecting that information. The next step would be to develop a water circuit. What's a water circuit? Well, it's basically an interconnection. It's a workflow of we call them nodes. Their structures could be an example of a node or a structure could be a dam, could be a pumping well, it could be a dewatering well, it could be a storage facility, it could be a whole number of things on a mine site. But all of those things need to be mapped, and we need to somehow quantify those those elements and how they're using water or moving water across the site. So we call that a water circuit. And the interesting part about a water circuit is traditional methods. We use something like AutoCAD to develop these visual elements and assign a static value to each one of them with lines that interconnect. The problem with that is that in no time they're going to be outdated because they're not dynamic. They're not connected to any type of source of information. And so this is the challenge around doing static water balance diagrams. Is they really, especially now with the demands and all the complexity around water, it needs to go into a data management system. And so what the third step would be is taking all of the data types, volumes, water quality, fluxes, you name it. You can add all this to the database. You have to normalize the database or the data itself into a centralized database that can, by the way, interconnect with existing databases. All of that information needs to be normalized so that it can be used in dashboards, in doing further analysis, and really gaining a better understanding of that water balance. And the key here is the interconnection, the dynamic nature of water and how it flows in a website or in a site is so important to really understanding how you're going to mitigate those potential risks. So step 4, heavily driven by operational needs and also corporate needs and of course, regulatory demands. We have dashboards that have KPIs that really show that balance. It's all pulled directly from a tool like Visual Water Balance and helps the operation really gain a deeper understanding. And not just an understanding, but it helps guide them into if there's an expansion. How much more water are we going to need? And then we can look at this on a map view and understand where we're going to get the water from and do further analysis and site characterization. So that is really my introduction to our water balance. I'd like to swing the mic over to Vinicius, who is our water balance specialist and visual water balance product owner. Vinicius, go ahead.
Hello, everyone. Thank you, Martin, for introducing me. Now I'm going to start to talk a little about the visual balance. So to overcome all this challenge that Martin told us, we developed the visual balance software. The visual water balance software offers a dynamic tool for the facilitated management of water balance. Here we can do in hours what currently takes days to do. All the problems that Martin told us, we can solve with this software. So the software consists of 3 different modules. Each module designed to help users visualize and manage different aspects of the operation water balance. So we have the module 1, the water circuit, the module 2, the maps, and the module 3, the dashboard. So the first module is the water circuit or flow chart. Here we can create and visualize the water circuit of the operation and the main data involved. Here we can represent the operations interactions with the water. We can connect the flows of the water to a measuring points or performing estimate calculations. We can identify inconsistencies in our water balance, gaps, and points that we need care attention about the water balance. And in this module, we can monitor and manage the water resources more efficiently. In the second module, the maps, here we can see the geographical visualization of water balance structures and their main data. Here, the software provides a comprehensive and detailed view of the water system in its geographical context. The software allows the identification of opportunities for new sources of water withdrawal for the operations and release this water. And here we can identify the operations interaction with neighborhood communities like the environment, the preservation areas, the indigenous communities, so we can see our water balance, our operation into a watershed context and all the interactions that we have. So the third module is the dashboard. Here we can visualize the main KPIs related to the management of the operation water resource. So the software has some pre-calculated KPIs like water use, water reuse, total water demand, water consumption, water release, water disposal, and the user can develop your own indicator based on GRI framework, ICNMM, and so on. Okay, now this is the visual balance software. So I'm going to use as an example a project that I created based on a real mining operation. So firstly, in the flowchart module, we have two main components, the structures, like these structures here, this box, and we have the flows that can connect the structures. So in each flow, we can see the volume or the flow rate that we are transporting, that we are using, or that we are working on. So here we have different types of structures of the mining. So we have catchers, dams, hydrants, mine pit, and ponds, precipitation, reservoirs, and so on. And we have different types of flows like exploited reused water, exploited water, transport, water use water, available water, reused water, and we have these types of flows here. In this example, we have at the top of this water circuit, we have a process plant that receives treated water from a river and a well. So we have a river here, a well here, a water treatment plant, and we have a process plant. And we have a equipment washer that receives water to do the process here. In the middle of this example, we have a reservoir that provides water to the dust control process. And the bottom of the last part, we have an open pit mine, which receives water from precipitation, and we have the groundwater here that we need to deal water in this process to advance the open pit process here. So inside the open pit mine, let me open. We have 3 wells that are doing the water process, and all the water that they extract is sent to our process facility, and we have some interactions here. And we have the precipitation interacts with the tailing dam, and we have water that goes a wastewater treatment plant and goes to a pond. So this is how the VWB looks like. So here we can see the volumes, we can see the delta volumes in each structure. So now this reservoir for this period of time has this volume. So now we can see the capacity of this reservoir here, and we have the amount of volume that we have on the reservoir, and we can see all the aspects of the water balance, how much water we have inside the open pit, and how much water we are recirculating here, how much water we have in the pond, how much water we are sent to a river, how much water we are consuming here in this process. So we have in detail all the features of the visual balance here. Now, I'm going to create 3 scenarios to represent the facility of the visual balance. The first scenario is in a climate change scenario. How will my water balance be affected? So let's assume that I will change the precipitation here. So now we're gonna have 2 more water comes into the open pit mine. So I'm gonna change the precipitation here. Now I'm gonna change this precipitation here too. Okay. So the software is calculating the volumes. Okay. So now we're gonna have much more water in open pit mine. We are send the same amount of water to our process facility in this example. In the reservoir, we have this amount of water, 25,000 meter cubics, but the capacity of the reservoir is only 22,000. So here we're gonna have an overflow of this reservoir, and all this precipitation will interact with the dust. We need to treat more water in this structure here, in this WWTP3. More water goes to a pound. So we need to, in the pound, we're gonna have more water than the capacities that we can hold in this pound. So now we can see how the process and how this amount of water, this growing amount of water, will interact with my flow. So I know that I need to manage these volumes here to face this problem, this new scenario. The second scenario is, what if an operation problem occur? So what if my well 1 is closed? I will disconnect this volume here. So let's assume that the next month we do not have this well 1 operation. So now we're gonna see these volumes, this average volume for March, and we're gonna see a negative volume that will be treated, that will need to be treated on WTP. So we have one only input here, this volume, and this volume we can't supply the amount of water that the process plant needs. So we need to think about how I can face this problem. So maybe I can bring water from reservoir, and in the visual balance is very easy to do. We only put the mouse in the top of the structure and push the flows. So now we can create this flow here to represent this scenario. So I'm gonna supply water from the reservoir to the process plant because we do not have enough water here. So, or maybe we can simulate like I'm gonna send the pound water to the equipment washer because we do not have enough water from the WTP. So it's very easy to upload in the VWB the flows. And if we have a flow station, a gauge station here, we can select the name of this station. So the VWB is connected into a database. So we can see all the stations that we have for this example. We can create an estimated calculation to do estimation about this flow here. And we can see how the water circuit will face this, how the VWB, how much volume we need to put inside this operation. The third example that I want to present is let me delete these flows here that I create. Okay. The third example here is, let's assume that we can't supply water. We can't send water to environments. So now we can't send this amount of water to the river. So let's disconnect this guy here. So we're gonna see on the pound that we have a huge volume inside the pound, and we do not have a capacity to manage this water, to storage this water. So we need to think about how I can manage my volumes here to another place or to another operation, to another structure, to handle with this excess of volume. So maybe I need to create another pound to store the excess of volume. So on the VWB, we can module this, we can create these scenarios, we can see what's going on in our circuit, and we can see how we can see how we can manage the water. The second module of the VWB is the maps. So here we can see all the structures into a map, and we can see the interactions with my operation with the neighborhood. So we can see a city or a preservation area. So we can see where I send my volume. So I'm sending my effluents here in these water cars. So we can see all these aspects of our water circuit, and we can see a resume of the volume. So we have this input volume and that output volume, and we can change the period of visualization to see the day that we want to see the volume. In the last module, we have the dashboard. On the dashboard, we have a summary of the KPIs the KPIs for the water balance. So we have the number of grants, the granted volume, the oil production of the mine. We can create the indicators that we want based on our water circuit or based on our flow chart, and we have some predefined KPIs. So we can see the water demand, total water, used water, reused rate, total water demand, and it's very interactive. So if we change the flow chart, we can change the volumes here. And we have a graph that we can see the accuracy in meter cubics of the type of our measurements. So if you have the volume measurement manually or automatically, we can see here this accuracy. So this is the visual balance, a software that we use to manage our water balance.
I hope you've gained some deeper understanding of visual water balance and just water balance in particular. And hopefully we'll see you at the next webinar. So once again, thank you so much. And we'll end it here. Have a great rest of your day and the rest of your week. Ciao.